Why is gold so valuable? People like gold because of its everlasting luster. It is not reactive with other metals or with non-metals. The death mask of Egyptian king Tutankhamun is made of gold, embedded with colored glass and precious stones. This gold mask is still intact today. The scarcity of gold is due to its non-reactivity with other elements or compounds. Metals with low reactivity such as gold, silver and copper have been known to humans from time immemorial. These metals are easy to remove from their compounds. Up to the 18th century, 7 metals were known. Metals with high reactivity such as potassium, sodium and aluminium have been known to humans for only a few hundred years. This is because of the complexity of removing these metals from their compounds. In order to separate the oxygen and to get pure metal, we must reduce the metal oxide by using a suitable reducing agent. We can classify the reactive series into 3 categories: the most reactive, moderately reactive, and least reactive. The earth is made up of rocks and minerals. A rock is made up of 2 or more minerals. A mineral is an aggregate of chemicals. Ore is a mineral from which metals can be profitably extracted. All ores are minerals, but all minerals are not ores, since we cannot extract metals profitably from all minerals. Ores are initially crushed, powdered, washed and concentrated by removing the gangue or dust by a suitable method such as washing, froth flotation, gravity separation, magnetic separation, etc. After ore dressing, different techniques are adopted based on reactivity. Highly reactive metals are separated by electrolysis of the salt solution of the metal. Moderately reactive metals are separated by roasting or calcination, followed by reduction. Carbonate ores are calcined and sulfide ores are roasted. Low reactive metals are separated by heating. The reduction tendency increases as we go down the activity series. The metals placed at the bottom of the activity series below hydrogen are not easily oxidized, and hence they are available as free metals in the natural state. Examples are copper, silver, gold and platinum. Their sulfide ores are roasted to give free metals. For example, copper sulfide is heated to give copper oxide, which on further heating gives copper. The oxides of metals placed below carbon in the activity series need reducing agents such as carbon or carbon monoxide at higher temperatures. Hence, zinc, iron and lead are reduced from their oxides by heating with carbon or carbon monoxide. Moderately active metals are usually present in nature as sulfides or carbonates. An example is zinc sulfide. Sulfide ores are converted into metal oxides by roasting in excess of air, and carbonate ores are converted into metal oxides by calcination, that is, by heating in limited supply of air, respectively. Zinc oxide is heated with carbon to reduce it to zinc. Besides the use of carbon, sometimes a metal displacement method is adopted. That is, a highly reactive metal replaces a low reactive metal. For example, high reactive aluminium replaces manganese from manganese dioxide on heating. During this process, an enormous amount of heat is released. We relax and enjoy the journey when we travel a long distance by train. We feel secure because we know that the railway maintenance team is vigilant in looking after the railway track. What will happen if we do not try to mend the cracks in railway tracks? How can we effectively repair these cracks? The thermite reaction is the solution. A mixture of aluminium and iron oxide is placed in the cracks in railway tracks and ignited. The ensuing reaction is called the thermite reaction. Molten iron is formed in a vigorous reaction. This iron hardens as it cools, welding the sections of the tracks together. This reaction occurs because iron and aluminium have different reactivities. Aluminium displaces iron, since the former is more reactive. The metals placed above carbon in the activity series are highly reactive. They are extracted from their ores by electrolysis. During electrolysis, reduction occurs at the cathode and oxidation occurs at the anode. Metals such as copper, zinc, tin and silver are refined to pure metals by the electrolytic refining process. A solution of metal salt is used as an electrolyte. Pure metal is used as the cathode and impure metal is suspended as the anode. On passing a current at suitable voltage through the electrolyte, the pure metal goes into the electrolyte and an equivalent amount of pure metal is deposited on the cathode. Soluble impurities go into the solution and insoluble impurities settle down at the bottom as anode mud.